Good morning, algebra physics class, and welcome to problem set 34, day 1, where we're going to be taking on the challenge of phase change and the amount of energy that it takes to change phase from one state of matter into another. The first thing I want to talk about is I want to talk today about the amount of energy that it takes to raise the temperature of gold to its liquefying point, and then the amount of energy it takes to change the state from solid to a liquid. So the problem here states the specific heat of gold is 129 joules per kilogram Celsius. Find the heat necessary to raise the temperature of 5.6 kilograms of gold from 124 degrees Celsius to its melting point of 1063 degrees Celsius. Find the heat necessary for the phase change from the solid to liquid. Gold's heat of fusion is 64.5 times 10 to the third kilojoules per kilogram. So as we begin this problem, the first thing I'd like us to take a look at is, in order to do question 1, we need to start with the specific heat of gold. Specific heat of gold is 129 joules per kilogram Celsius. And all of these particular problems that we're going to be doing today can be done by simple unit analysis. And so the first thing that we want to do is we want to be able to cancel out the mass of the bottom. So we know that we had 5.6 kilograms of gold. Man, I wish I had 5.6 kilograms of gold. That'd be worth a lot. Maybe I could melt it down and form it into something that I wanted to. But that would be kind of neat. Another thing that we need to know is we need to cancel out the Celsius. You can see in the unit analysis the Celsius needs to go, degrees Celsius needs to go also. So in order to do that, we're going to need to find the change in temperature. So I'm looking at the original temperature of 124 degrees Celsius. That's a very, very warm gold. I wouldn't want to touch that because remember, the fiducial point of the boiling point of water is 100 degrees Celsius. So it's above that. And we have to raise that all the way to 10 times the boiling point of water, up to 1063 degrees Celsius. So find the change in temperature Celsius. We're going to take the final minus the initial. So we're going to take 1063 minus 124 to get 939 degrees Celsius is the change in temperature. So we're going to have 939 degrees Celsius as what we'd like to put into our unit analysis. At this point, you can see that the kilograms cancel and the degrees Celsius cancel. So it's 129 times 5.6 times 939. We get a grand total of energy that it takes to raise the temperature of that, 67,836. Oh, excuse me, just a moment. Read my calculator wrong. 678,333.6. Now what we'd like to do is we'd like to melt the gold, go through the melting process. In order to do that, we're going to use something called the heat of fusion. That's a value that every single element, every single substance on the earth has, that is going to be the energy that it takes to change the state from a solid to a liquid. For gold in particular, it's 64.5 times 10 to the third joules per kilogram. Now we only have 5.6 kilograms of gold. That hasn't changed at all. So, but in the difference you'll see here is there's no change in temperature. It's like we talk about this. Usually we use a Cartesian plane to describe what's going on. And when you have the changes in state, you raise the temperature and then you melt. So this is change in degrees Celsius. This is melt. And then you have change in degrees Celsius. And then you vaporize. And then you continue back up. So they always have a plateau. I mean, we're talking about in the coronavirus, often you're seeing this same stuff being so important. And they're talking about flattening the curve. There's a natural flattening of the curve that occurs in the Dominion modeling of melting gold or melting water, like we're going to see on the next slide. So in this particular case, we're going to cancel out the kilograms. And so all that's left for the units is that of joules. So now I'm going to do a little bit of calculator work to find out how many joules it takes to melt the gold. So to melt 5.6 kilograms of gold, it'll take 361,200 joules, in case you want to know. Now I'm going to put my solution set down here, playing into the fact that I have 3 significant digits. It takes 6.8 times 10 to the 5th power joules to raise the temperature of the gold. And it takes 3.6 times 10 to the 5th power joules to melt the gold. There's your solution. We'll move on. Again, this question is the same basic concept, and I'm going to draw the Dominion modeling graph again. So for water, we know that at 0 degrees Celsius, it melts, and its other fiducial point is 100 degrees Celsius, and that's at where it begins to boil. Now, what happens with ice? The reason I really wanted to draw this again, you might be saying, Mr. Wilson, you just drew one of these. With water, it's very steep in the change of temperature from ice to 0 degrees. And then you have this plateau where it melts. This is ice. And then your slope goes down just a little bit for water. So there's a different specific heat for water. And then it takes a whole lot more energy to vaporize than for melting. We'll see that in just a second. And then it begins to take a steeper slope again, more steep than water. So that just kind of illustrates the specific heat and the change rate for water. So there's a few things that we want to do. The first is we want to do the ice change from negative 21 degrees, 0 degrees. And then we want to melt, and that's going to be done by the process of heat of fusion. And then we're going to change the water from 0 degrees Celsius to its other fiducial point of 100 degrees Celsius. And then we're going to, it could be boil or sublimate. Those are the two words we use for the change of state of matter from a liquid to a gas. And we're going to use heat of vaporization. And then we're going to change the steam from 100 degrees to 130 degrees Celsius. So the first thing that I'm going to do is I'm going to refer to the chart that I gave you in LMS, and that's something you'll probably want to have available for these types of questions, especially as we work here. You could kind of follow along and see what we're talking about. So the first thing I want to look at specific heat for ice, water, and steam. So you can look on the specific heat part of your chart, and you'll find the specific heat of ice to be 2,050 joules per kilogram Celsius. The specific heat of water on that same chart, you'll find this number to be very, very, very familiar. 4,186 joules per kilogram Celsius. And finally, for steam, will be 2,009 joules per kilogram Celsius. Okay, so you could see here how when it takes less energy to change the temperature of water, you're going to have a steeper slope on our Dominion modeling. That's why the steam and the ice should be a steeper incline. It's going to happen faster than it does with the water. The water changes about half as fast as ice and steam. And we've experienced that with something we're kind of familiar with. Now I also want to look up the heat of vapor fusion on the chart of water. And the heat of fusion of water is 334,000 joules per kilogram. Whoa. And the heat of vaporization, this is where it really a lot of energy is used, is in boiling. You've heard the phrase, a watched pot never boils. I always say with most of those little wives' tales that or sayings that old farmers use, or you've heard your grandmother say, there's always a little bit of science behind those. And that's the case with heat of vaporization. It takes a lot of energy to change a state from a liquid to a gas. So we're going to begin to work here on this particular problem. And it's just a matter of doing some simple unit analysis. But it's a good amount of unit analysis. So we're going to cancel out the kilograms by putting in 0.111. And then we're going to have the degrees Celsius. And so here we have 21 degrees Celsius that we're changing, and that was kilograms. So that allows me to cancel out the kilograms and the degrees Celsius. Now I just got to do a little bit of math, and we'll get 2,050 times 0.111 times 21 gives me 4,778.55 joules. Now we'll do this again for the melting. And this time, again, there's no change in temperature. So we're just going to put in the kilograms, which will cancel the kilograms, which will give me the joules. So we'll do 334,000 times 0.111 gives me 37,074 joules. What you're supposed to notice right here is the difference between those two numbers. It takes 10 times the amount of energy to melt the ice than it does to change the temperature of the ice. That's why come springtime, as you're driving past a pond, sometimes you'll see ice that remains on the pond for a long time, because it takes a lot of energy to change all that ice into water. Now we'll do the same thing as we did for ice for water, and we're going to change it 100 degrees. So we're going to say it's 4,186 joules times 0.111 kilograms times 100 degrees Celsius. And we got our solution to be 46,464.6 joules. And we changed that 100 degrees, and it was almost equivalent to the amount of energy that it took just to melt this ice cube. Isn't that crazy? And so we'll do the same thing for the next one. cancel out the kilograms, and we'll do 2,256,000 joules times our 0.111 kilogram ice cube. And this time, well, look at this number, 250,416 joules. No wonder it takes a long time to boil a pot of water. All right, and then we'll do the same thing for the steam. We'll do 0.111 kilograms times our 30 degrees Celsius. There's a mistake over here from the problem. We want to raise it to 130 degrees Celsius. So we're going to do 2009 times 0.111 times 30. 2009. That was back around the times I used to teach in a classroom. All right. And when we take that into consideration, it takes 6,689.97 joules to change the temperature of the steam. Now, I want to find the total energy it takes, so I'm going to add up all these numbers. So I do my 6,000, because that's one still on my calculator, plus 250,416, plus 46,464.6, plus 37,074, plus 4,778.55. And I get the number of a total 345,423.12 joules. And we take into consideration we were looking for two significant digits. It took about 350,000 joules to change the temperature. Most of that energy came from boiling. All right, let's move on. So this is a problem that we worked on last week. I know I didn't have a video for that, but I'd kind of like to explain this for you. One of the biggest things that going into electricity that you can remember is that V equals IR. Or another way I've heard it phrased so many times, volts equals amps times ohms. And this is kind of foundational for electricity. And then we get into, there's other equations that we'll use to calculate the amount of watts and certain things. But I hope you can really get into this problem here. The first thing that we want to do is we want to find the voltage across this 16 ohm resistor. And voltage remains consistent throughout an electrical circuit. So if there is 48 volts that start here, it's going to remain consistent throughout the whole thing. So there'd still be 48 volts down here as it travels throughout. So the answer to question A is 48 volts. And then it says, what is the current? Well, we know that we have 48 volts and we have a 16 ohm resistor. There's a symbol for ohms. And so we're going to be looking for I, which is found in the unit amps. So we'll take our 48 and divide by 16 to get that this is a 3 amp system. The current in this system is 3 amps. And the last question, question C, you're maybe like, Mr. Wilson, why do you keep asking us that? It says, what is the current that travels through the battery? What's the current that travels through the resistor? Again, that's going to remain consistent throughout, so it's going to be 3 amps again. All right, pretty simple problem. I hope that you're getting those. That's basically simple voltage and resistor and amps problem there. Now let's move on. One of these, we have buoyancy force questions that we've been working on. So what we have is we have a sphere that is submerged underwater. So let me get my little highlighter out so we can put this thing underwater. All right. So now let's tether it to a rope. And buoyant force is pushing up on this. I've seen it illustrated like this. In a liquid, we know that pressure comes in from all sides. And that pressure wants to push that sphere up. And it's just going to keep pushing up, pushing up, pushing up. Now, if we tethered that to a ground, so now you know what would happen if you took a pair of scissors and you cut the string of this ball, it would go shooting up in the air. We've seen that before. So the tension and the weight of the sphere is going to be holding it down, and the buoyant force is what's going to be pushing it up. So as we look at this, one of the things that I'd like to do is I'd like to find the volume of the sphere. And I've put this on a couple of slides now. 4/3 pi r cubed is how we're going to find the volume of that sphere. And what I'd like to also do is, well, let's just start with that. Let's just begin with that. So it says here the diameter of the sphere is 2.04 meters. So the diameter is 2.04 meters. And so the radius, I know some of you are going, Mr. Wilson, why'd you just do that on your calculator? I was just checking, is 1.02 meters. So we're going to put that into our problem here. Volume equals 4 pi times 1.02 meters cubed, pi r cubed over 3. So we're going to take our 1.02 and we're going to cube it. 4 times pi times 1.0612 all over 3. So then I can take that. I'm going to multiply it by pi. I'm going to multiply it by 4. Then I'm going to take that whole thing and I'm going to divide it by 3 to get an approximate value for the volume of 4.445 meters cubed. Now, if we look at this, we can take the density of salt water. I've tried to be kind of nice to you this year, and I really stated exactly what I'm looking for. And the density of salt water is 1,025 kilograms per meter cubed. And what I want to do is I want to put into play Archimedes' principle. And I've written this on a number of slides, that Archimedes' principle states that the buoyant force is equal to the weight of the water displaced. And so what we'd like to do is we'd like to find the weight of the water displaced. And weight is usually calculated in newtons. So my buoyant force is going to be equal to the weight of the water that's displaced. So let's start with the density of water. And we'd like to turn that into newtons. So we've got 1,025 kilograms per meter cubed. That's the density of salt water. And then we're going to take our 4.445 meters cubed. The beauty of that is it cancels my meters cubed. And then I'm going to multiply that by 9.81. And you've seen me in a number of videos. I say that, well, that's a Newton per 1 kilogram. But since like the first week of class, we have known that in order to get weight, you take mass times gravity in order to do that. So when we take and we plug this into our calculator, we got 1,025 times 4.445 0.45 times 9.81. The only unit that's left is newtons. So the buoyant force is 44,695.58625. Right? And so then the big part of the question here says, what's the tension? And we're supposed to be putting all the stuff that we've learned in physics together. And we know that Newton's second law says the sum of the forces in any direction is equal to mass times acceleration. We're going to make that 0 on the right-hand side because this ball that's tethered is not accelerating. Now remember, we cut the string. That's going to change the problem as the ball is moving up through the air. But at this moment, this is what we can focus on. So then we're going to look at first our positive force. The force pushing up is the buoyant force. And then pushing down is the tension. And it's also the weight, which can be calculated by mass of the sphere times the gravity. So we can begin putting stuff into this problem. The buoyant force is positive 44,695.58625. Tension is the variable we're looking for. The mass is 26, and the gravity is 9.81. Zero's still 0. I could just move tension over, so it's by itself. So that'll eventually, when I get that, it'll give me my solution. I'm going to do 26 times 9.81. Gives me 255.06, and that's in newtons. That's important because this also is in newtons. So my solution will be in newtons. Does that make sense? I hope so. So now we'll take the difference of the two, 44,695.58625 minus 255.06 gives me 40.526 newtons equals tension. So the final tension answer that we'll give when we put two significant digits into the problem is 44,000 newtons. One of the things, the 2 meters, I put that in every problem. Doesn't matter. So I don't know if you caught on to that by now, but I hope you did. I believe that's the end of day 1. Have a great day. I hope to see you, at least you seniors, at graduation, and everybody else I hope to see next year. Talk to you later.